Okay, now today, right, I thought we will do recurrent neural networks. Okay, recurrent. These are a little away from the ones, right, that, I mean, of course, they are also based upon same principles as we have already seen, but there are certain other things, right, that get involved when you talk about recurrent neural networks, some things that you have not seen before. And it's mainly used in language processing, okay, mainly, but doesn't mean that, it is limited only to that. Whenever, there is sort of a history, right, which you have to remember, there is a memory involved, right. You need this kind of an architecture. Okay, just that the architecture, right, has a name. I mean, it's called a recurrent neural network. And yeah, so whenever, right, I mean, for example, think about predicting a word, right. Suppose I gave you a bunch of words. I mean, this you often do, right, when you are kind of typing in, there is an anticipation as to what might be the next word. Right? That comes because of the history, right, and it's not just the previous word. There's also something before that probably happened, and something before that probably happened, right? Because of which it is able to predict with certain probability that maybe the next word that should come in is this, and then we take it or leave it, right? I mean, when we went through but the training, right, is such that it has seen lots of sentences, right, and something like a Wikipedia or something, right, from where you can take lots of sentences and then train, right, so that a network knows to anticipate, given that the past history was this. Again, there are lots of things. Okay, and this is a fairly deep topic, in the sense that how far past in the, how far into the past should one go, right? Where are all the important stuff? Because sometimes, right, something might have been said right in the beginning. For example, if you think about sentiment of some movie or something, right, and maybe something very damaging was said right in the beginning, and then, right, if you miss that, right, then you actually miss summarizing, right, what it is probably about. So, I mean, it's a little tricky, okay, but I thought here I just wanted to give you a flavor about what it is like, right, and just that, right, if at some point of time, right, if you had to do, I don't think we give you any assignment on RNN, right, we don't give you, but then it's good to know as to, right, how these things work. Okay, so in general, right, it's called like sequence to sequence learning. Okay, sequence to S2S to sequence learning. And it is because of the sequencing that you have a temporal ordering and temporal sort of a dependence and all that, right. So sometimes they call it S2S, right, sequence to sequence learning. Some examples, right, I'll give you just to begin with, right. Let's just take a few examples of where you might encounter these. For example, one could be language translation. Right, language translation. Like I said, right, I mean, many applications involve text, but doesn't mean that it's only text. For example, image captioning, or where, for example, the output is actually a text, but then the input is an image, right. So it's not like every time the input and the output both have to be text, but in many cases, right, you will have text coming in. So for example, let's suppose I say hello, how are you, right. Okay, if this goes as input, right, and then what you expect from the output, let's say it's in Hindi, then maybe, right, I might say namaste, aap kaise ho, or something, right, namaste, aap kaise ho, something like that, right, kaise hai, whatever, right, aap kaise hai, right. Well, I've forgotten my Hindi and all, but something like that, right. So that's like a language translation. So the input is actually right, is an English sentence, and the output is something like that, right? Namaste, aap kaise, something like that. And then you can have case like speech to text, right? This again, these are all things that you see around you, right? There's nothing unusual. Speech signal to text. So where, let's say, right, I mean, I get a speech waveform, right, that comes as input, and then maybe, right, it means something. Maybe, right, it just means hello, how are you? But then I want the output to be a text. Right? So input goes as a waveform, and then there should be a network, that should kind of analyze this waveform and give out an output that can be in a text form. Then there can even be what is called a question answering. See, this is again something that's very common. A question answering. So for example, I mean, yeah, it depends. I mean, there is something called a visual sort of a question answering. What it means is that I give you an image and then I ask something about that image, right? Let's say I give you an image and then say, what is, or, you know, what is a boy actually playing with? Your answer would be probably a one-word answer, you know, ball or something. Or you might say, what is the color of the dress the boy is wearing? You might say, whatever, red, right? It can even be sometimes a sentence, but typically visual question answering is like a one-word answer. You know, the output, I mean, a question goes in along with an image. That's like a, you know, a visual question answering. So you can also have a simple sort of a question answering, but more common is what is called VQA. Okay, a visual sort of question answering. Then you can have, like I said, an image captioning. Okay, and another example could be like image captioning, and that is also the reason, right, why if you look at the different examples, right, that I'm giving, that is also the reason why actually you've got different flavors of RNN. Okay, depending upon, you know, whether it is single output, multiple output, single input, multiple output, or multiple input, multiple output, right? Depending upon that, right, you can have different flavors. Okay, image captioning, right? This is another example. So in this case, you just push in an image, and then out comes a text. Right? So output is actually a sequence or a text. Typically, caption means it has to be some kind of a sentence, which we don't know, a bird flying over a body of water or something, or this, or whatever it is. Right? I mean, you want to summarize, right, what the scene is, or a boy is playing in the, you know, in the ground, something like that, right? So, and again, right, all of this will require some kind of training, right? I mean, it won't automatically happen. It's not like a human being, right, where we just look at an image and then we make interpretations about what is going on, right? So again, all this will require, that's the reason why what problem you attempt very much depends upon what is available out there, right? If somebody has created a data set where, you know, somebody, you know, kind of sat down and did a painstaking work of, you know, giving an image, producing a text corresponding to that and saying that should be the caption that should ideally come out, okay, and all that. But one of the things which you will also notice as compared to, right, things that we have seen earlier is that now you even need something like scores for, you know, a text, right? I mean, you're saying that a boy is playing in the ground. So you need to understand, I mean, how well is that as a sentence construction? I mean, would that have become bad, I mean, if I had interpolated the words or, you know, interplaced the words, right, in some other form, right? That might actually change the meaning of what is coming out and so on, right? So therefore, there's a lot more to it than just the simplified version which I'm talking about. Okay, so captioning is like, you know, image going out and then the output comes out as a sequence. Then you can have time series data, which is very, you know, which is very common, which you would have right in the beginning anticipated. Time series data, and so on. Okay, so one can think about so many places, right, where, okay, where let's say, you know, where you have this kind of framework, right, and it's not clear, right? For example, at this point of time, if I asked you, right, I mean, can you just use a CNN or something, or an MLP, right, that you've seen before, and could you have just solved all these problems with that? Then the answer from you would be like, I'm not sure, right? Because it's not clear as to how do you sort of, what do you think is really strikingly sort of, you know, this one, a different in these set of problems, right? Most, and let's say most of the ones that I talked about here, compared to what you've seen before. Till now we saw, no, we did CNN, we did MLP, right? We had a certain kind of input data going in, we were doing some training, there was a loss function that we had at the output. Just at a top level, right, if you were to think about what is probably happening here and why maybe such an architecture may not be of use, or, you know, cannot be directly, you know, employed, right, for a task like this. What would be the things that would catch your attention? Sequence, yeah. So a little bit.
We have an idea, some probability what is going to come next.
Mm-hmm.
Right? The boy then is like helping verb is going to come next.
Correct. Yeah. So in a way, so what you would call is there something like, just like, you know, we had things like, what do you say, right, before, you know, we had things like, you know, what do you call, dependencies and so on, right, local dependency and all we talked about, right? So is there something similar there? What you said is correct, but then is there a technical term that you can put in there that sort of encapsulates, right, what you're saying? A temporal, this one, a dependency, right? There is a temporal, this one, a dependency, which you didn't see till now, right? I mean, in all the things that we did, there was never a temporal dependency. Of course, if you had taken videos or something, maybe right at that point in time, you would have seen some kind of a temporal. That's why in fact RNNs are useful for that kind of temporal this one dependency. Okay, so one of the striking things is that you see already a temporal a dependency. And what others? Temporal dependency is one thing that's plain obvious that's going on here, which we didn't see before. Anything else? That will all have to be learned by the network, right? We are not going to specify anything explicitly, right? I mean, you could just take something like Wikipedia or something and take sentences from there and keep training. Another thing is that I think that you should definitely, you cannot miss this, the fact that the input and the output sizes or lengths, what is it? Are not fixed, exactly. Input and the output sizes or lengths or dimensions, whatever you want to call it, sizes, vary from example to example, are not fixed in the sense that they vary from say example to example. See, for example, sometimes you might have a long sentence for which you have a translation or something. Sometimes I might have a short sentence, again I need a translation for that, and there is nothing like a fixed dimension, right? The input can change its dimension, the output from example to example during training. Output sizes vary from example to example or from one example to another. Okay, so in a sense, right, these are kind of two striking things that are happening now, which we didn't see earlier. Now, there is just one thing, right, which I should probably mention, that is that when like I said, right, RNNs are mostly used for language processing, because in languages there is inherently a temporal dependency. Even though videos and all also have it, but mostly languages is where you have to capture a lot, and that's why, right, you need a representation. For example, when I give you a word, right, I mean I need some kind of a representation. I mean I can't just throw a word into a network, right? How do I even input a word, right? So there should be a representation, right? Now that representation is typically done using what is called a word to vec. Okay, this you will see, I mean, or there are even other say representations, but something word to vec. What it means is you convert a word to this one a vector. A vector means it's like a set of numbers. You see, finally you can only train with numbers, right? I mean, you can't do anything else. Network has to understand how to read numbers. Now, what is done is, I mean, right, we are not going to go into how this word to vec is formulated and so on, but the idea behind word to vec is that, right, when these words occur, right, there is always an interplay, right, between the words. When some word occurs, there is typically a bunch of words that occur right around it. I mean, if you go through text, really watch very closely. All this has to be, of course, captured. We can't manually sit and do this. So this word to vec is actually something like that. I mean, it's actually a network by itself, okay, which has been trained over lots of data, and where it understands the relations between words, right, when something occurs. So it's like saying, right, in a space, okay, if I have a feature representation for a word, then I need a representation for another word. If that often occurs when this guy occurs, then I would need something which is kind of close to this representation. Right, because these two sort of seem to it looks like when this occurs, that guy inherently also occurs, or occurs let's say 2 words before, 3 words, depending upon how far away, right? I mean, do you follow that? So it's like it can't be like one is here and one is way elsewhere, but then actually they do have some kind of a closeness when they actually appear in actually sentences, right? So that is what this word to vec actually captures. So it's a set of real numbers. Okay, it's not like a one hot representative, because one hot representative will completely miss out this kind of a relationship. I mean, you might ask, why not I have a one hot vector, I'll have 1 0 0 0, dog, maybe I'll have 0 1 0. If you do like that, right, then you don't capture this kind of a relationship that actually inherently exists. Okay, because words don't occur at random, right? Sentences are constructed based upon something, right, based upon certain rules, and therefore they have a spatial or they have a relationship in some sort of feature space, and that is what this word to vec captures. Okay, so from now on, whenever I write a text, let's say I say the boy, a boy, right? So boy will be like a word to vec, right? So you should understand that there are a bunch of numbers that are going in, and that actually means that those numbers actually have a representation. That means that that's a very nice representation. It's not just a one hot vector. It's a nice representation that actually encapsulates the what, all. So if you look at the vector representation of words around boy, you will see that, oh, maybe when boy occurs, ball probably occurs, and that's for ball and boy, right? If you see that vector representation, there will be somewhat similar. Otherwise, you will just throw away all this relationship and build something which is which is not very meaningful. Okay. So this word to vec is something, okay, that we will always remember that we can do. There are other representations also, but just keep it simple. Okay, it's called word embedding. Okay. Okay, I'm not going to through that. Okay, so then, right, so in a general way, right, if you talk about RNN, then it looks like what can go as input, right, is x1, okay, all these examples, okay, x2, and then xt, okay, xn minus 1, xn, and then output can be like y1, y2, and then yt, okay, and then so on. Okay. Now, see, one way to right, think about this is that, I mean, why can't I have, for suppose, right, see, one of the simplest ways, right, I mean, in which, right, you might be able to handle probably this variable length and all that, right. What you could say, not variable length, let's say one way to let's say, right, in a very naive way, right, if I had to do an do this RNN, what I could do is the following, right. So I take xt minus 1, which is my input. Okay, then I construct something called ht minus 1, right. I mean, I will talk about what this ht minus 1 is. Then I have something like, okay, now from here to here I transform it using a matrix, let's say ut minus 1. Then I have ot minus 1, which is my final output, and then this I transform this ht minus 1 using some matrix vt minus 1, and maybe there is a bias and so on. And this is actually an MLP. Okay, the MLP, right, which you already saw. So this ht minus 1 is itself like u times ut minus 1 times xt minus 1. So there are a bunch of weights out there, and there is a bias out there, and then maybe, right, there is an activation sitting out there, and therefore, right, you get your ht minus 1 like that. And then on top of that, right, you can have your vt minus 1 is another thing that is acting on top of that, and then you have the output layer which gives you your ot minus 1, right. So this is what we understand as an MLP, right. Now then I take the right next input, which is like xt, and then for which, right, I can have a matrix ut, and then, right, I kind of produce an output ot, and then vt. Okay, there will be another matrix, and then maybe next instant of, okay, this is ht. Then at the next instant of time I get an input xt plus 1, and then I multiply it with ut plus 1, then I have vt plus 1, and then I have an output ot plus 1. I can do this, but then, right, I mean, one of the things that you clearly notice is that this kind of a temporal dependency, right, it's not able to encapsulate, right, it's not embedding that. Right, I'm not able to see that something that occurred in the past is being used in order to make a prediction about the next output. For example, OT, right, I don't see how, let's say OT, right, OT, it looks like whatever XT comes in, it is just acting on XT and then doing something. It is not even, it's not taking the history into account. Right? That is one thing. And the other thing that is also looking a little jarring is that these weights, right, will tend to blow up, because every time, right, you have ut minus 1, then you have a different matrix which is ut. All these are weights, right, finally. Then you have vt plus ut plus 1. So this should be ut plus 1. Okay, and so on. So here see, parameters definitely don't look like, right, and the other thing is that how many MLPs do you need, right? I mean, so each is an MLP now, and it looks like I'll have a varying length, right? Sometimes I may have to use more, sometimes I may have to use, because my input length can be actually varying, right? I mean, here of course, here I have a kind of a synchronous thing. It looks like I'm asking for every input, right? I'm asking for an output. Sometimes it can happen that I watch the entire thing and then give only one output, right? Something like action recognition, right? So I will watch the whole video. I mean, I can't just put out an action for every frame, right? Action recognition is something like, I have a video, so I have to go through all the frames, look at what is happening, and then finally output something. I will say it's whatever, it's some action, running, jogging, something, right? Now, so here, so that's why, right, RNN can have different flavor. It doesn't mean that every time you will have a setup like this. But the simplest which you can think about is this, right? For every input that's coming in, maybe, right, you are asking for an output. Okay. but then right, clearly okay, it doesn't encapsulate this. And the other thing, so right, the weight seem to be a problem. The I mean, the variation in the size seems to be a problem. And third is a dependency, right, is not being encapsulated. So there are various versions of this. I won't go through them, but eventually, right, what kind of one sort of, you know, one settles down for, right, is this structure, okay, which is like this, which is the okay. So you have xt minus 1 again going as input, then you have u. So the dependence on time is gone. Then you have ht minus 1, okay, ht minus 1, okay, ht minus 1, and then you have a v, and then you have ot minus 1, and there is a connection from here to the next, this one, which is ht, and this takes xt, and this is again u, this is again v, this is ot, and then again you go like that. Then you have ht plus 1, then again the same u, then the next input xt plus 1, ot plus 1, and so on. So now what has happened, right? Most of the things that we said are kind of handled here. One is one is the weights, right? So which part have you used here? Which property, right, have you used here in order to reduce the number of weights? We're just weight sharing across time, right? We're just using the same bunch of weights. We are not changing the weights, right? So it's like weight sharing that we talked about when we did a convolutional neural network. Something similar to that. We don't change our weights. We are just sharing the weights across time now. We just keep them steady, constant. Oh, sorry, and there is a w here. Okay, there's a w here. That's also a matrix of weights. And the other thing, right, that we also seem to be doing is that. Okay, now, right, I mean, in a way, right, what you should kind of, you know, look at this effectively, right, given the, okay, now the other thing is a temporal, this one, a dependency, right. I mean, that you can see is happening because of the fact that, right, this one, okay, this quantity that you have here, right, I mean, it's called actually a hidden state, or it's called the state. And this kind of, right, encapsulates whatever happened. It's like a summary of whatever has happened till that point of time. See, for example, right, I mean, you know, if you look at ht, right, ht seems to depend upon ht minus 1, and then it seems to depend upon xt, right. But ht minus 1 in turn, right, depends upon xt minus 1 as well as ht minus 2. And ht minus 2 in turn, right, will be a function of ht minus 3 and xt minus 2, right. So in a sense, if you just look at if you unroll it, right, if you unroll in time, you will realize that till whatever point you are, if you look at this state vector, which is like, you know, ht minus 1 or ht for that matter, that has encapsulated all the information coming from the past. It is supposed to, right, we wanted to encapsulate all that information coming from the past, and take this new information, right, which is your new xt that is coming in, and in a sense, right, make an say estimate now. And you know, this is not anything very new. Okay, by the way, if you have done a Kalman filter or something, right, it does exactly that, right. I mean, have you done a Kalman filter where you have a state equation, you know, which talks about how the variable rate evolves over time, you know, as a function of itself. So for example, right, you can think about a smooth motion, right, of some object. Now that could be a motion model, right, that you have, so that even if you don't observe anything for some time, right, this happens when you're doing target tracking. A target goes, right, I mean, you know, there is a cloud which kind of obstructs your view of the target, right. So there is no observation at that time. You don't see it at all. But then you will have a motion model which will say that even if I have a very weak observation, I will still go strongly by what my motion model says, because this guy was moving. Therefore, you don't expect it to suddenly stop somewhere, break off. If it breaks off, it will go wrong. But typically that motion model will actually predict. So this kind of a prediction, right, that's happening is coming through this ht. So the ht is sort of saying that all the past, right, history, right. So I mean, you know, in terms of tracking, right, it'll be the motion history of that particular point or something. Whereas here, typically it's for languages, right. So it's like this, like the history of the sentence or something, or it could be a video where the history of the temporal action of the video is evolving, and I mean, right, if you've done say HMMs and HMMs, right, I mean, what are called hidden Markov models, they have all used these notions, okay, hidden state and all that, okay. So the hidden state is something that is supposed to encapsulate information coming from the past, and then you have to use the current input and then make this one, a prediction, okay. So that way you've been able to take care of the weights, right? You don't have a blow up, and in a way, right? I mean, this a succinct representation of this, right, is this. So you can think about this as H, and then W, and then X, and then U, then V, and then O. So in a sense, right, what is happening is you are just using the same MLP again and again, right, as this input keeps occurring. That's what is going on, right. The unfolded thing, this one unfolded in time is what I have shown on the top. That's like unfolding it over time. But really what you have done is you are just reusing the same MLP, right, as one input comes in other. So that way, right, you no longer, right, I mean, you no longer have an issue about say varying lengths. See, by which, right, by varying lengths again, right, what you have to kind of realize is that I can have a sentence that consists of 5 words, let's say, for which I need an output. The output again can be 6 words, 10 words, we do not know, whatever it is, right. I mean, but the input, the next time, right, I might have an input that has probably, right, 8 words in it. That's another sentence, right. So now you don't need to a priori know what should be the length, because, right, that was a problem that we saw initially. I mean, how many should I put there? But now, because of this rolled up sort of an architecture, which is why it's called a recurrent structure, right, because it's recurrently acting. And therefore, because of this recurrent nature, what will happen is we don't have to worry, right. If an input is 5 words, then this recurrence will happen 5 times. Sorry, not word, input sentence. Even for a word you can have, right, if you count in terms of the alphabets and so on. Or if you have a larger sentence, it will automatically, right, act, right, that many times and so on. You see the point, okay. So in a sense, right, so the RNNs have actually memory, okay, that's something that we never saw before, have memory, and they are called a recurrent because they perform the same task, called recurrent, as they perform the same task for every element in the sequence, every element in the sequence. So it's like a chain of repeating modules, right.